So in this example, we're going to prove an identity using what we've developed with the derivatives of these functions. So for instance, here we want to prove the identity that tan inverse x plus cotangent inverse x will equal to pi over 2. So what we can do this in a couple ways, but one way is I'm going to let f of x equal to the left side of this equation. So tan inverse x plus cotangent inverse x. And we can then take its derivative. You know, tan inverse of x was 1 over 1 plus x squared. And the derivative of cotangent, remember, is actually the same thing but negative. So when I add them together, we'll get 0. And it'll equal to 0 for any value of x. So something you remember is that if I have a function whose derivative equals to 0 for all x, what does that mean? Well, that means that f is a constant function. And that's exactly what we have here. We've shown that f prime of x will equal to 0 for all x. Therefore, f of x is a constant function. In which case here, we could say that f of x must equal to some constant. Here, let's call it c. And what is this value of c equal to? Well, we could really just plug in any value of x that we choose, and it should always equal to the same value for c, as long as we can evaluate it in each of these functions. So, you know, one easy choice might be to do something where both, this should be cotangent, not cosine. So choosing something where both tan inverse x and cotangent inverse x are defined. So let's say pi over, let's do f of 1. That's an easy one to choose here. You could do f of 0 or f of negative 1, but here let's try f of 1. So we know that tan inverse of 1 will equal to pi over 4. And we know that cotangent inverse of 1 actually is also equal to pi over 4. So that gives us pi over 2. Notice we would have gotten the same thing if I chose any other value. Say I tried f of 0. We get tan inverse of 0 plus cotangent inverse of 0. Well, we know tan inverse of 0 will be 0. Cotangent inverse of 0 will be pi over 2. So that also gives us pi over 2. So whatever value of x we choose to plug in here, we'll always get pi over 2. So there we have it. Tan inverse of x plus cotangent inverse of x will equal to pi over 2 for all x. Let's practice with some integration. Remember these formulas we've discovered for finding the derivative of sine inverse or the derivative of tan inverse. We can now use them to help us do integrals. So if I see an integral that involves a function of the form 1 over the square root of 1 minus x squared, I know the antiderivative of this function must equal to sine inverse. Or similarly, if I've got the integral of 1 over 1 plus x squared, we know the antiderivative of this function is tangent inverse. Now let's try an integral of the form 1 over the square root of 1 minus 4x squared. Well, with a little bit of algebraic manipulation here, for instance, I could rewrite this a tiny bit into a form that might make it easier to set up for integration. Say, for instance, I want to substitute this value here where we've got 4x squared. Well, if I rewrite that as 2x in parentheses squared, now I can see that we can replace the 2x with u, and then we'll have something in the form 1 over the square root of 1 minus u squared, which is exactly the form that we know the antiderivative for. So that's what we'll do here. We'll let u equal to 2x, and then du will be 2 dx. So we'll get a 1/2 that comes out from the substitution. And we see what remains here is now in the form 1 over the square root of 1 minus u squared, which we know that's the integral that'll give us sine inverse of u. Okay, now in the original problem we had the limits of integration went from 0 to 1/4, but let's quickly rewrite those. So when x was 0, we get u would be 2 times 0, so it would be 0 still, that one stays 0. And when x is 1/4, we get u would be 2 times 1/4, which is 1/2. So we get the upper limit would now be 1/2. So it goes from 0 to 1/2 now. So that's what we'll evaluate, from 0 to 1/2. So it'll be sine inverse of 1/2 minus sine inverse of 0. And if we remember sine inverse of 1/2, we want to think what angle would give us a sine value of 1/2. I think that would be pi over 6. And then sine inverse of 0 would be 0, since sine of 0 is 0. So our answer here would be pi over 12. In this example, we've got the integral of 1 over a squared plus x squared. And in this case, a is sort of a random constant that doesn't necessarily take on a particular value, but here we can sort of think about how this will manipulate into a form that we can integrate. So one little trick I want to remember is that in this case it's similar to this form, right, where we know this will be equal to tan inverse of x. But we want to get a 1 there instead of a constant a squared. So the trick I'll do is I'll factor an a squared out. And so that'll be left with a 1 plus x squared over a squared inside. Okay. So just that little factoring trick now gives me something that's closer to the form that we can integrate. But before I get there, I want to think about what to substitute. In this case, I can write 1 plus x squared over a squared as x over a quantity squared. And now it looks to me like this would be a good choice to substitute x over a. So if I let u equal to x over a, then I get du will be 1 over a dx. And so the a times du will become dx. So therefore this integral becomes 1 over a. And then here we've got the a from the substitution, so times a. And then 1 over 1 plus u squared du. We can divide out these a's in front, and we get what's left here is just the form that we know is going to give us tan inverse. So this will be tan inverse of u. And therefore this will be oh, sorry, I messed up here. So this should be a squared, and so I should have a 1 over a left over here, right? Sorry, let me fix that. So we just canceled one of those a's. So over here, we'll actually have 1 over a tan inverse of u. So we'll have 1 over a tan inverse of x over a. So it's sort of a more general version of this formula that we have up here, that if I have something of the form 1 over a squared plus x squared, the integral will be 1 over a tangent inverse of x over a. Here, let's see how we can manipulate this one a little bit. We've got the integral of x over x to the 4th plus 9. Now looking at it, it's not quite in a form where we can use that tangent inverse formula, but it looks to me like maybe we can play around with it a little bit to get it into that form. So for instance, x to the 4th, I'm going to try and rewrite that as x squared squared, because now it appears that if I substitute x squared, we can get rid of the x up here. So that'll be a nice little substitution trick that we can do. We're going to let u equal to x squared. So that'll substitute the x squared inside the parentheses here. And then we get the derivative is 2x dx, and so we get a 1/2 du will replace the x dx that we see in the numerator there. And now what we see is more of the form that we saw in the previous slide, where it's 1 over u squared plus a squared. So we can compare this. This is like our a is 3, right? So it's 3 squared plus u squared down here. So if I use that basic form that we showed in the previous slide, the integral of 1 over 3 squared plus u squared will be 1 over 3 tan inverse of u over 3. And then here, putting our u back in, 1 over 6 tan inverse of x squared over 3. So just a little bit of manipulating it to get it into a form where we can substitute something to form that tan inverse integral.